Hello everyone, this is your TA speaking Arthur, and we are going to be covering the midterm 2 review material for this semester, spring 2020. As you can see here, it says UDP, TCP, congestion control. There should be flow control here. Data plane, control plane, IP. There is no ARP that will be covered in the network layer. That will be covered in the link layer. DHCP, NAT, and ICMP. Trace RT should be something that you do in your own time. If there is less than an hour of this video, then we will also be covering it. But I'm sure none of you are actually going to be watching a 1 hour video, so I want to do this as fast as possible and as dense as possible. So it's likely we won't be covering this in today's video. I already have this open, but UDP, this is slide 4 by the way. So we have UDP here. Now I'm sure if you really want to, you could have just already read through all this, so I'll be only covering the what I think are essentials for you to remember. And what that is, for this part of the slide, is UDP is unreliable and connectionless. So as a consequence of that, you have these other talking points. Alright? Because we are unreliable and connectionless, we have to give best efforts. And what that means is explained down here, is despite the fact that UDP packets may be lost or delivered out of order, it will still attempt to deliver it as best it can. And if it's a vital, packet from client to server or server to client, then it will resend. It's just that whoever is receiving the UDP packet will not know until it gets the packet. Another thing of note is that UDP, along with TCP, is the last end-to-end protocol that we will be covering in this class. And that's somewhat important as we progress into the network and physical layers. What else do we have here? Oh yeah, also as a consequence of being unreliable and connectionless, we no longer need acknowledgements and sequence flow control, and pretty much congestion control as well. Within the transport layer, because if you think about it, the only reason we can have congestion and flow control is because we have these acknowledgements and sequences, but because we are an unreliable protocol, we do not have acknowledge and sequence numbers. Ergo, to create a flow control and congestion control mechanism, we'd have to use another field in the header, or develop a new field. If we go down here, as you can see, the header for UDP is only the port number, destination port, source and destination port number, the length, and the checksum. Each of these, as you can see, are 2 bytes or 16 bits long for a sum total of 8 bytes. In terms of networking, everything is almost talked about in bytes, except when you're working with ISPs, because they like selling packages of what they call internet deals. So when they say that you have like 100 megabits per second, that's it's not very much in terms of megabytes, obviously, but it sounds good on paper, right? Or it looks good. But in actual networking classes and when you're working with it, everything should be calculated in bytes. Unless you're working, of course, in the physical and data layer, where you're developing the frames and all that stuff, where everything will be bit by bit checking, but it's still working in bytes as well. It's just how you are checking things. Alright. Aside from all that, what else was in here? So you can read through the rest of this, but again, the main thing to remember is it's unreliable and connectionless. And because of this, all of these are a consequence of these 2 things. Does that mean UDP is worse than TCP? No. They just have different uses. Another thing of note in this entire slide is remembering what a socket is. A socket is the IP address plus the port number. And everyone should know what a well-known port is and what an ephemeral port may be. Understanding that concept is not essential to this class, but it is key to understanding how protocols work in the transport layer and how you could have multiple different connections at once if you want to get into networking or just further your knowledge of the topic. Let's see, again, connection list best effort. Why is there UDP over here that explains that? Okay, again, we're going back to here. What is important to recall is that UDP has an 8-byte header, not 8-bit. Previously, there have been people who have put 8 bits on exams, and that's not right. Remember, these are 16-bit header fields. As you can see, there's 32 bits total in each row, and each field takes up half of it. Ergo, these are 16-bit each, right? And so 16-bit is equivalent to 2-byte. There are 4 of them total, so we have 8-byte total. Why do we need a source port number and UDP header? Optional, 0 if not used. I wouldn't specifically test this. It's nice to know, but I don't think, excuse me, I need to drink water for a second. I don't specifically think that the professor or I are going to test you on this specific amount of knowledge, because we aren't writing the netcode for UDP in here, and it's more important for you to understand the what's inside the header than how to set up the header itself, at least in my opinion. This is a Wireshark capture, Wireshark captures. If you don't understand how Wireshark captures work now, please send an email to me or Frank, and we'll try our best to help you. But again, this is something that you really need to play around with yourself to digest it. And so let's go down here. So UDP checksum and the zero header, or the pseudo header, I'm sorry. The pseudo header, well, first let's go over the checksum first. Okay, down, there should be a slide on this. Yeah. So in the checksum, as explained here, we are trying to get all zeros. And the reason why we're trying to get this is because calculation-wise, it's very easy for computers to do zero comparisons. If you know anything about, or if you are a computer engineer, you know that in the hardware layers, we basically hard program and design a zero flag check. In a software, you can also do that essentially the same way, which is what the transport layer runs on. So it's always good to do checksums, which will eventually equal 0. And so I'm not going to go into extravagant details, how they figured out and made the formula for all of these. You can read it up on it if you want. I'd highly recommend it. But to basically go through it, we're going to give you a value, and this is the message, or what it may be called, and you're going to want to do a bitwise addition. Now this is hexadecimal, but if it's easier for you, you can convert everything to binary. But as you can see, you are doing byte by byte addition here. So, oh, not byte by byte. I'm sorry. Is it byte by byte? No, yeah, it is 2 bytes addition. So, 99F3 comprises of 2 bytes. 4427 comprises of 2 bytes. 2396 is 2 bytes, and E3 and 4F are 2 bytes. In other words, it's 16 bits, right? So, as you can see, 99F3 plus 4427 plus 2396 plus E3 4F is going to be equivalent to 1E4FF. And we move the carryover to the very end, and that's going to give us E500. And then we take a 1's complement of this, which gives us 1AFF. Now if you notice here, if you add this value, right, the 1's complement to the value before it, you will get all zeros. So 1AFF is the checksum, right? And E500 is the message as explained here. Now, if you don't know how to do hexadecimal addition, it's fairly straightforward. It's like all addition is just in the base 15, or I'm sorry, base 16. So right here you have 3 and 7, that's 10, and then whatever 10 is in hexadecimal, then you add on that 10 from this value over here, which is going to be a 6, and then over here, which is an F, and so on and so forth. You carry over, which will give all this. Now you can do that all on paper, and it's very straightforward. If you can do this example, which basically has all the steps, then you could do any checksum that we give you. In fact, I believe when Frank wrote the second midterm 2 semesters ago, he used this exact example. So we aren't going to give you an actual message that could be very, very long. It's just going to be something of this size. Socket programming is something that we are not covering in this exam explicitly, but the concepts are important to know. So the idea here, where we have the client and server both opening a socket, and then the server basically binding their socket to one of their ports, and then actively or passively listening essentially to incoming requests, whereas the client opens a socket and then it doesn't really bind in this case because it's not TCP but it's rather UDP, this particular socket, but it does send a message using this socket. I guess you can say it does bind it in a sense, and that socket is now considered a UDP socket because data coming to and fro from the client to the server and server to client will also be using that socket purely for UDP. But it's not like the server where that socket will always be a UDP socket, if you understand what I mean. So that's what that bind is doing. That bind is saying this socket will, or rather this port will always be a UDP port. The client does not do that though. The client just picks a port and then creates a socket out of that port. And until the duration of this connection is over, it will just be a UDP socket. And that close basically allows that port to be reused for another socket. And this is basically the same for almost every language here. Python, as you can see here, is actually easier to read than the C and C++ versions of it because you only have function names, whereas these are fairly readable. Let's see, everything else is, yeah, these are just conceptual things that would help you understand how UDP works. I wouldn't say study it religiously, to phrase that way, because we are not going to be testing you, or at least I won't be writing any questions regarding specific stuff for coding transport layer code. So we are going to skip 4A. Let's look at 4B. Anything in here? More socket stuff. So we're going to go straight to TCP. So in TCP you have the end-to-end connection, and again, TCP and UDP, or the transport layer, is all together is the last layer where end-to-end protocols will be covered in this class. So again, you can read through all of this stuff. You know, it's very long. It's actually not as condensed as the textbook slides, but what do I want you to take away from here? Very first thing I want you to take away is, unlike UDP, it is reliable, right? And why is it reliable? It's because we use acknowledgement and sequence numbers. What does that do? Why does that make that reliable? If you guys remember in class, if we go down, let's not use that image. Alright, let's use it here, or to this slide. When, let's say, the client is requesting something, and this is the server, it will send a packet. And the server will acknowledge that it received this packet in its return packet and send an acknowledgement plus the data requested, and vice versa until we get the close. And if we have a lost packet somewhere in any one of these, the acknowledgement and sequence numbers are going to be out of sync. And as a response, both sides have their own method of correcting this. In the client side, we resend the requested packet if the data that we were sending was dropped, or the request packet was dropped, because the server will be sending acknowledgments from the previous packets, which says, hey, I received, let's use this here, 789, but I want 10 next. But previously, the client had sent 7, 8, 9, and 10. So in that case, you will only be sending acknowledgement 9 if you're the server, and the client will thus respond by resending packet 10. And that's basically reliable data transfer in a nutshell. Both users have a pre-agreed upon method of ensuring that each packet was successfully sent and received. Now going all the way back up, what else do we have here? Efficient flow control. That's basically what is also happening there, but we'll go into that a little bit further into this. Streamed oriented buffer. So we're gonna have to go back down into another image to go over that. Right here, the full duplex buffers. Okay, this concept may or may not be tested in your exam. I would say it is an important topic to fully digest, though. If you do not understand the full duplex transmitter and receiver buffers, I think even if you pass this class, you failed in networking. This is very vital to understanding TCP, and I honestly don't think if you fail to understand this concept, you will be able to understand TCP at all. So each side maintains their own sending and receiving buffers. If you didn't know, TX stands for transmission, RX stands for receiving or receiver, and those derivatives of those words. But in this case, the client is transmitting data and the server is receiving data, which is why here we see the arrow sequence 33 plus data 100, which is what this indicates here. All of this data is going to go to the server, and the server sends an acknowledgement 133 because that is what it's expecting to get from the client in the next transmission from client to server. Okay? Now, in this case, we have the client as the receiving buffer and the server as the transmitting buffer, right? I think Frank messed up on his slide right here, but the idea maintains is the same here. We are sending data. These arrows should be switched, and ignore these numbers. I don't think he yeah, these numbers aren't right at all. Hold on, where's your sequence of 133? Okay, so we are taking from this, but we're acknowledging 133. Yeah, I don't understand why Frank is using the client transmission buffer in this one down here. This should be reversed, and these values should not have be of the same values of these buffers up there. But yeah, so the idea is still the same, it's just vice versa. The server is now transmitting, the client is receiving. But I'm sorry about this page right here. I'll talk to him about editing it and then re-uploading the slide. Okay, and then this is the same thing just with no values. So sequence data plus the acknowledgement, and then it sends the sequence and data, and then it acknowledges it, and then it sends its own sequence of data, and then that gets acknowledged back. Okay. Piggyback. Do you need to go over with this? Okay. Piggyback, transmitter receiver buffer pointers. What this slide is trying to refer to is the fact that you do not have to send separate sequence and acknowledgements, or yeah, sequence and acknowledgements in separate packets. If you remember in your Wireshark captures, if you've looked at the flags being set, you'll always see the acknowledgement flag being set in every subsequent packet after the very first SYN packet. And this is pretty much what this is referring to. When you receive the data, or when you are sending data, you can also acknowledge the previous data being sent to you. And this is what this is basically. Okay, we have flow control. Hold on, before we get there, is there anything else that we can go? So I already went over end-to-end stream-oriented buffer. Okay, that was the flow duplex. So we can finally go through flow control and congestion control. Where is it? Oh, right before we get into over that. Three-way handshake, if you guys don't remember, is the client opens a connection, a socket in this case, and sends a singular SYN packet. Okay, and what actually is occurring here is no data is being sent, and the SYN flag is set, but there's no acknowledgement set. There's only one bit that's set in the flags, and that's SYN. And so the server, which should have a open socket passively listening for any incoming connection, will get this and then send a SYN ACK. And typically for all three of these connections you will have no data being sent. Typically. Is it possible? Yes, technically you could do it, but for almost every single connection in the world that uses TCP, I can guarantee you for almost every one of them there will be no data being sent in the three-way handshake. And this really comes down to just wasted resources or resource management. So if you send a payload with your initial request, your SYN packet, right, and you drop, for whatever reason it gets blocked or dropped or whatever, the client, if you remember the buffers down here, has already then preloaded data or preserved resources on its machine for both data going out and data coming in, if you get what I'm trying to say here. So if for whatever reason there's a holdup, or the server doesn't immediately disclose that it's closed or whatnot, the client is basically reserving resources that could be used elsewhere. And so there's no reason to do that. So instead, we send minimalistic packets to ensure that a connection can be established, which is what this SYN, SYN-ACK, and ACK is doing. Nothing besides these flags are being set so that both client and server do not waste time setting up and reserving resources and basically the buffers, so that, you wait an entire 1 minute for any connection coming to and fro and nothing comes, and you go, well, you just wasted one connection's worth of resource. So Yeah. Uh, if a million of them happen at the same time, and your half of them are just basically wasted connections, that's going to be a lot of downtime for the other half a million users. If they got the same, or another new half a million users. And in terms of cybersecurity, that can be used as a method of attack as well, but we're not going into that now. And this flowchart is basically the same thing you're seeing here. So the green is the server. So you begin. It's closed right now, the socket. And if we open the socket, it passively listens, or in this case it says passively open, and it's just waiting. And the moment it gets a SYN packet, it sends a SYN-ACK right here. That's what that is. And then it sends an acknowledgement when it receives the actually, is this the client? Is this the server? Right, this is the server. Yeah. So that's what it receives. This is what it sends, and then it also sends it also gets the acknowledgement from the client, and then there's an establishment. I'm sorry. When I always look at this for the first time in a while, I get sometimes confused. But yeah, so that's what that is. So the green again here is the server. So the I guess you could say very light purple, or maybe, yeah, this is purple. I was gonna call it pink, but this is the client here. Okay, where it is happens, you begin, you active open, which is what is happening here, and you send a SYN packet, which is this state here, right? And once you send that, you're expecting a SYN-ACK, which is what this flowchart says here, and as response, you send an acknowledgement, and so you get the established here. Now, in the case that both the client and server send a SYN to each other, they both must send SYN-ACK. Because again, in the client-server model, we just differentiate who is client and who is server based on who is sending the request. So if both client and server are trying to act as a client, then they both must send a SYN-ACK, which as a consequence, actually, they both are just on a open port, waiting for one or the other to send data, and basically they time out. It's very rare for this to happen nowadays, but this is something that used to happen fairly often in the pre-2000 days, I would guess. But the main paths are: this is the server going SYN, SYN-ACK, ACK, and this is the client going SYN, SYN-ACK, and ACK. And so these are the close that you see here, and these closes are not super vital for you to remember each one, but you should know at least one. Like this, if you get the SYN and you send a SYN-ACK, but for some reason the socket is closed, then you send a FIN, and then the acknowledgement, not the socket, I mean the client closes and sends a FIN, then you send the acknowledgement and you just close and you time out there. Likewise, if you're established and then one of the client or the server attempts to close the connection, you send a FIN, and then they can send a FIN as back, and then you send the acknowledgement, and then they send the acknowledgement. Or you can send a FIN-ACK and you get an ACK. So basically it's either double FIN, double ACK, or FIN-ACK, ACK, and then a double FIN and a singular ACK. Those are the main three ways. There's another image here that I think further down that shows the exact same thing. Yeah, right here, TCP connection termination. So these are all the same ways. You might find this one easier to find out, but I, in this semester, am not going to write any questions regarding all of the connection closing. What I will be doing would likely have a question that includes closing a TCP connection though. It might be part of a bigger question, or it might be a standalone. Oh yeah, they're all there too. But it is important to know at least one. Okay, so we have, oh, this is another important concept to understand, the sliding window. There's there are YouTube videos with animations that show what the sliding window is referring to, but it's useful for understanding flow control. If you can try to see over here, let's see, if we send 7, 8, and 9, right? Then, or just go over here, if we send 8, 9, and 10, the moment the server sends the acknowledgement for 8, 9, and 10, the buffer will slide essentially across to 11, 12, and 13. But let's say that we send 8, 9, and 10, but only receive the acknowledgements for 8. Then the buffer is going to slide to only 9, 10, and 11. And basically that sliding window is the metaphorical limiter, I guess you could say, or part of the buffer that is being maintained until you receive the acknowledgement for the data that was just sent. And this sliding window is also in the server side or the receiver side, and that is the receiving window size, if you know what that is. I believe that's talked about down in here. So this is the receiver buffer and then receiver window. And that's basically the same idea here. The window is essentially a sliding buffer in the sense that you have data that's completely reserved, right? In this case, let's just go with an arbitrary 100 megabytes. And then the receiving window is basically how much data you can take in. And so the TCP data in buffer, in this case, is the TCP data that has not yet been completely acknowledged. So as the acknowledgements go out, and that this receiving window will increase. Will increase. But as data comes in, this spare room is going to decrease. And that's basically what I was trying to get at. If you look at a animation, it might be more clear to you, but in my opinion, I dislike the basic animation that's shown because those are very ideal cases. If you recall, the job of a router is to dump packets as fast as possible. And if you also recall, there are things that there's the cumulative ACK. Okay? So it is possible, right? It's highly unlikely, but it is possible for a client or a sender to send more data than was previously acknowledged. And so the window will be basically held up by a previous acknowledgement that has not yet been sent out for one reason or another. Now, does this situation happen often? No. Are you going to be tested on this? No. But I think it is important to understand that what you see in this class is not gospel. What we're trying to teach you is the basic of networking. And because of that, I want you guys to understand that we can't cover every single situation that may or may not occur, and that all these protocols are not perfect. They're not perfect. They are not foolproof. There are issues with them, and one of those issues, in this case for TCP flow control, is what I just described. Things like this can occur, but it's important to understand why they occur and the consequences of them, or the consequences of consequences of how the protocols were created, which causes them. In this case, flow control works because we use acknowledgements and sequence numbers, and we allow for cumulative acts. And because of this, we can have situations where we have a lingering piece of data in the receiver buffer that has yet been acknowledged. But because there's space in the receiving buffer, the sender may pretty much step out of bounds in this case, in the sense that it didn't wait for the acknowledgement and send the data prematurely. Now, it depends now on whoever wrote the code and how they handled it, but protocol dictates that this should not happen. But can it happen? Yes. But again, protocol dictates that it should not. Again, there's a lot of things there's a lot of stuff in networking that protocol says one thing, but as a consequence of writing that protocol in a particular manner, you have some fringe cases that exist like this, such as also in the simultaneous open. Protocol dictates that when a machine in a TCP connection receives a SYN, it sends a SYN ACK. Now, this is a consequence of how protocol dictates TCP connections. Is it necessarily bad? Well, not really, because nothing actually happens and the connection will automatically close by itself. But it is a consequence of how protocol was written and is written and how code works. So again, all this is just me emphasizing again that there are fringe cases within these protocols that do exist, that either one, we cannot go over, and or two, as of right now, like, it would take too much time to explain. I think I've been going on this rant for about 5 minutes, but the basic thing the thing I want you guys to take away is, don't take our word as gospel. Our job here is try to give you all the information you need to understand the basics of networking, and in this case, in TCP flow control, I believe that it is important to understand that fringe case though, because if you just go purely off of what protocol dictates and how people create animations and talk about the subject, you may not realize that if in the future you're working on TCP protocols, that such a case could occur, and understand why it is occurring. But that is my opinion. Oh, and here's the sliding window, essentially what's occurring here. This is talking about the cumulative acknowledgements that I was just talking about. And you guys can read all of this. The main thing to take away from flow control, if you don't recall though, is that the receiver, controls the flow. And the reason for this is everything is being sent to the receiver first. And since they are the one receiving the data, and potentially from multiple sources, they must also be the one who controls how much data is sent to them. Because again, all of this is resource management. In the class, we use singular examples, but I also want you guys to start thinking in a bigger scale. If you're running a company like Amazon and you're going through several million transactions in a day, right? Are you going to maintain 100% uptime? And if you are, how are you going to maintain it? And this is something that you have to consider when you are writing this kind of netcode and running these kind of connections. You have a limited amount of resources to use, and so you can only offer so much space, in this case, the receiving window size is the advertised space that the sender can basically send to. So if you want to send 1000 megabytes worth of data, but the receiver only has 100 megabytes, you can only send a packet size of 100 megabytes. And that's all you get. Okay, TCP header and pseudo header. So the TCP header is very important to this class. And so is the UDP header, but the UDP header is very simple. The TCP header, not so much. There's a few stuff in it, a few more things. You have the source port number and a destination port number. Now again, these are port numbers, not IP addresses. Alright, I don't want you guys getting confused in the exam if there are questions about this. But just remember, the transport layer talks to the application layer. It receives data from the network layer. Vice versa, the transport layer sends data to the network layer, depending on which direction you're going on the network stack. And therefore, there must be a method of communication in some form or manner, right? So with the application layer, the transport layer talks through port numbers. But in the network layer encapsulates the data from the transport layer. So when we are creating a checksum though, why do we need, if we have it in here, why do we need the, it's in here, the IP address then, and the source IP address, destination IP address, 0 protocol, all that stuff? Well, I believe I've said this before, but historically, the TCP header and the IP header was basically one entire thing. Now, what do I mean by that? I mean that the transport layer and the network layer was essentially combined back in the DARPANET. But as we phased out into what is known as the internet today, we separated these into their own distinct layers, into their own distinct jobs. As a result, though, there's lingering, essentially, consequences excuse me, of having the TCP header and likewise the UDP header rely on a pseudo header to do checksum calculations. And this is because there are invisible leftover fields, basically, from when the two were still one. But it's not the entirety of it. You're just using set fields, which are the source IP address, destination IP address, the protocol, and TCP length, and 0 is just pads, to calculate and ensure that the checksum's right. Now I want you to notice in the IP header there's a protocol field. Now just because the network layer encapsulates the transport layer, it still needs to be able to send the encapsulated data to the correct transport layer protocol, and it uses the protocol field to do that. So despite encapsulating the data, it still needs to talk to the transport layer through the protocol field. It's not really talking though, it's just sending it through. Whereas the application and transport layer, I guess you could say they have a real conversation in the sense that they are actively talking to and fro because they are end-to-end protocol layers. Whereas in the network layer, those are hop by hop. Alright. So you aren't really doing a lot of talking per se. It's just to ensure that when you finally reach your destination, you send it to the correct handler of the protocol, so that if it's TCP, you don't get a UDP packet, and if it's UDP, you don't get a TCP packet. Okay, we go back into here. So this is the receiving window size. It's 16 bits. Acknowledgement number, sequence number, and acknowledgement number are 32 bits long. Source port number are 16-bit. Destination port number is 16-bit as well. Right? And then the header length is I don't remember how many bits in total. This is padding. These are all the flags. The checksum. This is the pointer to urgent data, the options, and the application data length. So all in all, if you include from source port number all the way to pointer to urgent data, you have a total of 20 bytes worth of data. Alright, so a TCP header can be at a minimum 20 bytes. And if you include all the options, you have a maximum of 60 bytes. So a TCP header can be between 20 to 60 bytes. Likewise, an IP header can be between 20 to 60 bytes. So, what else is important to know in this? Well, I'm not going to test you on all of the flags, and they are fairly straightforward flags as well. But if there are questions on it, either through revisions or Frank adding one, just know that U is for urgent, A is for acknowledgement, P is for push, R is reset, S is SYN, and F is FIN. Right? And as the name suggests, if you set the urgent pointer, then you're claiming that your data is urgent. It must point directly to this packet and be sent out first. If you use the acknowledgement flag, it's saying I'm acknowledging a previous incoming packet. A previous packet that was received, and your acknowledgement and sequence numbers will reflect that. If you use push, you push the particular packet to the front of the buffer. When you're I can't remember what top of my head what it is right now. But basically, when your network driver, reads the packet and reads that bit set, it will send it to the front. Reset obviously terminates and resets the connection. SYN and FIN are self-explanatory. SYN is the very first packet that's being used, and FIN is the very last packets that you should be receiving or sending. One thing to note is that when you are only sending a SYN and FIN packet, because there is no data being sent, you must therefore increase the sequence and acknowledgement numbers by 1. Now, the reason for this is because, again, when you are using these flags by themselves, you have not sent any new data, nor are you acknowledging any old one. So if you had just sent them by themselves without changing the sequence or acknowledgement numbers, by protocol, you should be resending the previous packets, right? Because if you remember, if you are sending packet 789, right, but the server only acknowledges 7 and 8, you should not be able to send packet 10 until 9 is acknowledged. Again, that's by protocol. That should be what occurs. Now, could other stuff occur? Of course other stuff can occur. And this is one such case where that other stuff is important. If you are sending a SYN or FIN packet, the sequence and acknowledgement numbers are not changing. Therefore, the sender should be resending that packet, and so you would be going into an infinite loop. Therefore, the protocol tells you you must add on to the sequence and acknowledgement numbers. Obviously, the sequence number would be the one increasing by 1. It would stay the same, but the acknowledgement would be requesting +1, and then the the third packet, the final one, would be the +1 sequence number. And we'll see that in a later example if I have time going over the midterms. But right now, that's just an important concept for you to understand. You will go into a cyclic or an infinite loop if you just follow pure protocol. That's why they changed it so that you must maintain a sequence and acknowledgement number +1 every time you use these two flags by themselves. Checksum is the same as UDP. Receiving window size is the number of bytes the receiver can accept. Pointed to urgent data, it's only used if the urgent urgent flag is set. And optionals, we're not going over them, and everything else in data. Okay, so you have the receiving window size. Okay, so you can receive data out of order. This we go over when we're going into the network layer. But for TCP, technically you don't receive data out of order. But in the network layer, when you are breaking packets into segments, you can receive the segments out of order, and then those will be, reassembled to give you the packet. These are the the flags, what they mean. Initial sequence number. Oh, right. So MSS and ISN are kind of important to know. MSS is the maximum segment size. MTU is the maximum transmission unit. So MTU is used when we are talking about really in the network layer, because that is more directly related to what link layer, physical and data link layer protocols are using. I don't think we're going to go into them at all, but just know that if you're using like Ethernet, you are limited to a specific frame size, and that as a consequence limits the network layer packet size, which has a minor effect really on the segment size in the transport layer. Oh, sorry, I've been talking a lot. Throat's kind of getting dry. Okay, and so the MSS is greater than the MTU because of fragmentation. Again, these effects kind of cascade, but because of the way they work, how we separate logically the layers, MSS and MTU don't necessarily have a direct correlation all the time. But when we go down into the link layer, we may go over how the link layer protocols directly limit the MTU. But these aren't, MSS is not going to be something explicitly tested, or something I at least will not explicitly test you on, but it is nice to know. ISN, on the other hand, is something vital for you to understand. It may be tested on, actually, now that I talk about it, because an ISN, or initial sequence number, is important for the security of a connection. So while security is not something that we actually exam you on for this class, so technically you could pass this class without knowing it, I want you guys to understand it because we may be giving you a question similar to this image right here, where we give you an initial sequence number and you have to work with that. Now that doesn't mean that there's a payload being sent, that's just the sequence number. Alright, so it's important to know that your payload starts at 0 always when you're opening a connection, but your sequence number may not be 0. So this is the TCP close. Again, these are fairly straightforward. Either you have a fin-ACK, fin-ACK, or a fin-fin-ACK, or a fin-ACK-ACK. I don't recall if there's a fourth one, but there might be. It eludes me at the moment. But you can just follow through this entire flowchart as well. But just remember just one. At least just one. It's fairly straightforward. Again, when you use fin by itself like this, um, even with a when you use fin by itself like that, you should be increasing the acknowledgement number right here. So let's say this is 25 in this sequence number right here. You should be acknowledging 26, and then this will be, let's say, sequence 20, and so you acknowledge 21. And that's it. The connection closes. Okay, this is all going through that. This is a comparison between UDP and TCP. This is something that you can look at yourself. But what is important in here is mostly what I've already said. There's some other stuff that the professor might add on to my exam that he might test you on, which is how many connections can you have in UDP and how many in TCP. UDP, you can have a multicast or a unicast or just a broadcast, whereas in TCP you must maintain a one-to-one connection because you need to have a reliable connection. And to have a reliable connection, you cannot have multiple sources connecting to a singular user at the same port. Okay, that's unicast only. And that doesn't mean that a server cannot have multiple connections to different users. It just means that each user cannot connect to the same point in the server. Whereas in UDP you're just sending stuff. So because of its very light nature on the network, all users can send to the same thing, or the sender can send, or multiple people can send to the same user in the system, or vice versa, etc., etc. Let's see. Again, there's optional checksums in UDP, whereas in TCP it's required because it's reliable. You have the buffer tube stream buffers. Where else? What else? Kind of, I wouldn't say super important terminology for this class because we kind of just muddle everything together. But UDP, you have datagrams or datagrams. In TCP, you have segments. Typically, this is the way it goes, though. In the physical or data link layer, you have frames. In the network layer, you have packets. In the transport layer, you have segments, or in UDP's case, you have a datagram. And in the application, you just have data. And that's all for this slide. Let's opened up. Well, oh, that's why. That's its own slide there. And this is talking about the retransmissions. Let's see what else is here. And timeout and RTT. Okay, so this is a relatively, actually very important. This is talking about congestion control. This is retransmission and congestion control. So again, this is what I am talking about here, where you have the case where the host or the client sends data all in one. 92, you get acknowledged. You send 100, no acknowledgement, and then you send sequence. As you can see here, you have the acknowledge of sequence 100 afterwards, and this says, hey, I got to sequence 100 and I'm waiting for it. That's what this acknowledgement is saying. The client had already sent it, but because the server is saying I am still waiting on 100, we have a resend of that data. Alright? Now, the very next thing that will occur, or rather should occur, is because the client already sent sequence 150, right, and 20 bytes worth of data, then the acknowledge will not be 150 now, but instead 170. Why? Because we already received 150 plus 20 bytes worth of data. So we already received all the data between 92 to 169 in this entire sequence. If you follow what I'm saying. If not, just look more closely. We have 92, sequence 92 plus 8, so we acknowledge 100. We have 100 plus 50, that doesn't get sent through. And then we have 150 plus 20. The server is requesting 100, or when sequence 100 starts. So we resend sequence 100 plus 50 bytes worth of data. So the next logical step would be to go to sequence 150, which has 20 bytes worth of data, which the server already has. So we go to 170 instead. So it's acknowledgement 170. Alright, and now we have a timeout. So timeout is related to RTT. Okay? So in this, we have 2 bytes, not 2 bytes, 2 packets, or rather segments, being sent out. In this case, we have them coming into, right, this timeout when they were sent during this timeout. So in timeout 1, right, at the very beginning we sent sequence 92 and 8 bytes of data with it. The acknowledgement was sent after timeout 1's time had ended. Pardon me. Thus, the client has to resend this data, even though host B technically has it. The reason why is because we must maintain a specific time frame in which both the client and server can maintain a connection if it's being used, and if it's not, will automatically close. This is what timeout is used for. And this is helpful for congestion control as well. We'll get into that in a second. But in this case, the timeout, as you can read here, is too short. So we need to go into what is the optimal timeout value, which we get into the RTT measurement. And this is all what this is talking about here. So how do we measure RTT? And in this case, you have a cumulative act scenario, and this is premature timeout. But you could read all of this. What I want to get into is right here. Now, some of you guys, when we were going over this in video, I think struggled to comprehend what was going on in it. But it's fairly straightforward. You have this equation here. You have an estimated RTT and then a sample RTT, right? And then you have a term alpha. Now alpha is just a given value, a value you assign. In this case, alpha is typically a value of 0.125. Excuse me, sorry. And this is just your estimated RTT, which is built upon a sample RTT. Now this sample RTT is an actual measured value. Okay. The estimated RTT is, as the name suggested, something that you are estimating. You are predicting this. This allows you to have variable RTT, so it's not static. The reason why we want a variable RTT is because imagine a connection that is initially not very busy. So you have a very short you want a very short RTT, right? Because if the network is not busy, then RTT should be very small. But then as the network gets busier, we would like a larger RTT in case a packet is forced to go through a longer route, right? And if the packet is being forced to take a longer route, then the RTT is obviously going to be longer. So if that is the case, if we have a statically bounded short RTT time, you will likely always occur a timeout. So this is why we have a dynamic RTT. In this case, we call it the estimated RTT. So you have the sample RTT likely from a previous connection, and then you guess an RTT, right? And this is also, it's either, if it's the very first connection when a computer boots up, it's either going to be 0 or it's going to be an automatically assigned value depending on whoever writes the code. And then it will give out some number, alright? And then that will be your new estimated RTT. Now, if the packet that's being sent falls within this estimated RTT, then everything is working as intended. And we will simply recalculate, right, the value of the estimated RTT based on its current value plus the actual RTT time. And we are going to give it some given weight right here. This is a percentage to each one, and then that will be the new estimated RTT. And so this is how you have a dynamic RTT. You're sampling both the actual RTT and a estimation of what you expect the RTT to be, and then giving values to both sides to try to have a smoothed out RTT line. Let's see if we have a image here. No, there are no images in this on this slide, unfortunately. Let's see, setting the timeout. Again, this is basically the same thing. Yeah, but this is essentially the same thing. So the equation is just slightly different, but beta is the same. Case is an alpha in here, where it's a weighted value essentially. And then you have the sample RTT and estimated RTT, and then the derivative RTT. So and then you're doing all this, and it's just basically buffer space, safety margins. But the equations are straightforward to understand. Will you be tested on this? I want to say no for the equation part. Will we be testing you on the concepts? Very likely, but I wouldn't say. If we give you a question using these equations, we will give you all the values, and that's basically that, or at least most of the values, and then you would have to solve for one. But I don't see a way out of like giving you all the information you need and just wasting your time, because all of this is we would have to give you all of the given value here, and then you solve for either estimated RTT if we give you this equation, or dev RTT, and then the only other thing we could tell you to do is like plot it out, but that's just a huge time sink. So I would highly suggest just understanding the concept of what timeout is, and how we get a dynamic RTT, and just not worry too much about the equation. I would highly suggest that. exponential RTO, or retransmission timeout. This goes into play when you have multiple timeouts. The reason why we have exponential RTO is in the event where you could have multiple timeout back-to-backs, it's better pardon me, to delay sending packets rather than congest the network further. So exponential RTO backoff is just saying, hey, we had one timeout here, and very likely we will have another timeout, so let's wait X amount of time before sending the next packet. Now, not all TCP protocols, congestion protocols do this, but we aren't going to go over all of them. Just know that that is something that does occur. You can just read it straightforward. We're going into congestion control as well. Congestion control is very straightforward though. The congestion control is only controlled by the sender. The receiver does not care about congestion control in the direct sense because it is only advertising to the sender how much data it can hold. It's up to the receiver to figure out if it's taking too long between each packet being sent, or otherwise each RTT, and adjust accordingly. The receiver can only tell the sender how much data it has. It should not have to maintain that type of information, because then we would run into a bigger issue of more logistics. So, down here, we have two types of congestion control: network assisted congestion control, and then end-to-end congestion control. So network assisted congestion control is not at all covered in this class. That in itself could be, that is a lot of stuff to go over actually. But we're just going to be covering end-to-end congestion control, and in particular congestion control only by TCP. So what do we have here is very straightforward. We have the sender sending data, right? And we're using the MSS in this case, and a congestion window as well. As you can see, we increase the congestion window by one segment every RTT until we have a loss detected. In this case, a loss could be a timeout or a duplicate ACK. Alright, now a timeout again is when your acknowledgement goes outside or is received outside the scope of its assigned time to be received. Whereas a duplicate ACK is when you receive two ACKs within the same time frame, or two or more ACKs. So throttle the sender. So here's what you should take from this slide: slow start, congestion avoidance, congestion window, and threshold. Now the terms additive increase and multiplicative decrease are, I would say, kind of important to know. Those are, I won't say, they're very, those are just very specific terms, I would say. And we're not testing you specifically on being able to use those terms. But slow start, congestion avoidance, congestion window, and threshold are terms that we will be expecting you to know. And here we go here. Now over here we have slow start being explained, where it's basically an exponential increase of sending or increasing the congestion window. So we start out with 1, get acknowledged, go 2, get acknowledged, then go to 4, get acknowledged, etc., etc. And then that's being multiplied every time. So as you can see here, 1, 2, 8, 16, 32, 64, 128, 256, etc. until we can no longer get it. Now this is congestion avoidance right here. Now in congestion avoidance, what we're trying to do is prevent a basically timeout event from occurring. So here, and it's always going to be 1. You're always sending at least 1 packet at all times if TCP is being maintained. And the reason for this is even if the receiving window is 0, it will not always be 0. And so you always want to be sending 1 byte of data at least to ensure that the moment that window is no longer 0, that the connection is still being maintained and you can send more data afterwards. So first we start out at 1, then 2, then 4, then 8, etc. So this is slow start, or an exponential start, if you will. And really it's called slow start because we're kind of testing the waters. These jumps are, exponential in growth, obviously, but at the same time, this is not a continuous exponential growth. This is just testing the network to see if it can handle a certain amount of data until we reach the previous threshold. Now in this image, this threshold was from a previous connection not shown on screen or in the textbook at all. We just assume it to be the threshold. Now the moment we hit the threshold, we stop going into slow start. And again, the reason why we call it slow start instead of exponential start is because we are trying to hit that threshold. It's basically if, let's say, 4 and 8 are not 8, we hit 4 but we can't go to 8, the new threshold would be 4, right? And so then we go 1, 2, and then we attempt to reach 4 again. So as you can imagine, if there's a heavily congested network, it's not really a very fast way. It's a very fast way of finding out the threshold and the network congestion, but it's not a very consistent way of starting or sending out data. You're just guessing, essentially. And so that's slow start in a nutshell. You are basically testing to see if we can reach the threshold. And then the moment we hit the threshold, we do a linear growth. We are sending 1 maximum segment size each transmission, and then we increase the congestion window each time it successfully is sent. If you don't recall, MSS is max segment size. And then the moment that we hit a timeout or triple duplicate ACK event, which is essentially a loss event, we do one of 2 things depending on the congestion avoidance protocol we are using. In TCP Tahoe, we immediately drop down to 1 again. We count any loss event as a complete loss, and we dropped immediately down to 1. The same thing occurs in Reno. Alright? These are the only 2 congestion avoidance protocols we're going to cover. So TCP Tahoe, we go through slow start, then we do a linear build up, and then the moment we hit a loss event, we sent the congestion window back down to 1, and then we do slow start again, and etc., etc. Whereas in Reno, we have a thing called fast recovery. Now, fast recovery is just basically, okay, we dropped to, we have a loss event. Now, if this loss event is a triple duplicate ACK, right, not a timeout, if it is a triple duplicate ACK, we go to half of the threshold. or I mean, not half the threshold. We go to half of the current congestion window size. So in this image right here, the congestion window is 12. We hit a triple duplicate ACK, and so we must go to 6. And so once we hit 6, we are basically checking for a triple duplicate ACK event. And that's basically how the textbook describes it. But really what we're doing is we're just doing a linear growth. And we do this linear growth until we can actually, let me rephrase that. We cut the congestion window in half, right? And then we do linear growth. Now in the event that the very first packet also, right, gets triple duplicate, then we go from 6 to 3, obviously. And then if that occurs, then we go from 6 to 2 and then 2 to 1. And that's only in the case for TCP Tahoe where we get triple duplicate ACKs. If we get a timeout event, in the timeout event, we immediately go to 1 like in TCP Tahoe, because there's no recovering from a timeout. If there's a timeout, that means that the network is severely congested to the point where we can't even send and receive data. Whereas in TCP Reno, I'm sorry, in a triple duplicate ACK, what that's saying is, hey, the server at the very least had time to receive some data and and send 3 ACKs in the same time frame before timing out. So it's possible that we lost, the segments somewhere in the network, where the packets were lost somehow. So the network may not be as congested as we think it is. But just in case it is somewhat congested, in TCP Reno, we're going to do a fast recovery. So we're going to cut our congestion window in half, and then we're going to and then we're going to linearly grow our congestion window again. And it is very straightforward. So slow start is an exponential growth, just to test the waters. The threshold is the previous the threshold is the previous position where everything was basically fine. And then in Reno, you can get a fast recovery, which will go to the half the current congestion window, whereas only in a triple duplicate ACK. Whereas in Tahoe, regardless of a triple duplicate ACK or a timeout event, it will immediately go to 1 congestion window or 1 MSS. Okay. Whew. There's a whole lot of talking there. So here you answer some basic stuff here, but just note that if we give you a question on congestion avoidance or TCP congestion control at all, it's going to be something that you've seen, like this image here, which is directly from the homework, or something that is something similar to this. Or it will be a short response question, but this is something that's definitely going to be tested. Okay, this is congestion control in a nutshell for just the flow control. Whew, finally, we're going into IP. I gotta say, I've been talking for a while. I feel like I've been talking for an hour. Now, if this is an hour, I apologize to everyone. But that's just the way things are. Going through everything one by one by one by one. Alright, so we're heading into IP. Now, IP is the beginning of the hop-by-hop protocols. Alright, so what do we have in the network layer? I'm sorry, not IP, network. IP is just a particular protocol in the network layer. I apologize. So we have routing protocols, the forwarding table, the IP protocol, and then ICMP protocol. And these are the 3 main cruxes that are covered in this class. There's a lot of stuff to go into the IP, but first let's go to the actual IP itself. So I'm skipping over data plane, control plane, pre-routing, all that stuff. I'll go over that later. So in the introduction, first and foremost, the only thing we're going over is IPv4. Okay, IPv4 has 32-bit identifiers, and that's the IP addresses you see right here in the image and commonly see that are not hexadecimal. Oh my gosh, I am tired. I've been talking for way too long. And this is fairly straightforward. I think if you read through this, it should be easy to understand. What is an interface? The interfaces is each connection that a host has that for a particular network. So you could have multiple interfaces. Let's say this is a router. A router can connect these two different interfaces, and then these interfaces can have their own subnetworks in it. So this router has two networks on it. And then here you see that the same thing I was talking about. You have a LAN, and a LAN is a local area network. So here we have 3 LANs and connected all to one host. And let's say that this host is a router, or it could be a network switch. And that's as straightforward as it gets. Pardon me. The main thing to take away here is that IP addresses are hierarchical. They have a network ID and a host ID. And the network ID is used to identify what network that a IP address is on, and then what host it is assigned to. And that a host can maintain multiple different networks within it. And that IPv4 networks are 32-bit longs. So at the very beginning, the conception of what the internet is today, we had classful addressing. And in classful addressing, we had class A, class B, class C, class D, and class E. And the way we identified it is the beginning bits. If the very first bit, the leading bit, is a 0, we have a class A address. And then over here, if the leading 2 bits is a 1 and a 0, then we have a class B address. Over here, if the leading 3 bits are 110, we have class C, etc., etc. And so we don't really use classful addressing anymore, but it's just this image is important to know for the concept. First concept, we have a network ID. As explained up here, we have network IDs. And this network ID is the first byte, or the first octet, right? And then the subsequent 3 bytes are the host ID. I'm sorry, I don't know what came over me. And then in the class B, we have 2 bytes worth of network IDs and 2 bytes worth of host IDs. In class C, we have 3 bytes worth of network IDs and 1 byte worth of host IDs. Alright? And so this obviously will cause problems, because if you have a class A address, you have more hosts, which means you have more IP addresses you can assign to a device. So everybody would love to be a class A address. But class A is very pricey and is only given to a few people. So we developed new techniques and we got rid of classful addressing to get more devices onto the network. Now, the second thing I want you to take note of this image is the all 0 address and the all 1 address. Now, when you have all 1 in your host bits, that means that you are broadcasting to everyone on the network. Okay? When you have all 0s on the host bit, then that means you are referring to the network itself. Okay, so these are reserved hosts, and if you have all ones completely and all zeros completely, that means you are broadcasting to everyone in the internet, and you are referring to the very first, or your very device, essentially. Pardon me, I need a drink again. Okay, and that's really what's more important, though, just understanding that when you have all zeros in a host and all ones in a host, you're either referring to that network, or you're referring to the broadcast address for every host on that network. Again, we have an issue of unnaturally and unfairly allocated hosts for the Class A and Class B. So what do? We go into subnetting and CIDR. Subnetting is very straightforward. If you recall, everything related to computers is related to bits, and so you can have a maximum of 2 per each bit, right? A 0 or 1. So the idea is, if we maintain the class full addressing, right? In this case, in this example, we have a class B address. We have the network ID of 141 and 14, right? But if we take 2 bits from the host ID, right, and tack it onto the network ID, we technically have more hosts. We technically have more networks. But as a consequence, we have less hosts to assign. Now, the reason why this would be useful is if a company could not get a Class A address and had to settle for a Class B address, but wanted to split their network into, let's say, accounting and HR, then they could use subnetting, in this case, to easily split off multiple sections of their company. Okay. And then this is supernetting, which is the reverse, where you give up part of your network ID to assign to your host ID. And all of this is only occurring privately, which means publicly, when you are connecting to an IP address, all of this does not matter. Okay? You are only getting whatever was bought or assigned to you. But the moment that a user connects to your network, you reroute them to your subnet or supernet network and host via that way. But don't overcomplicate what subnetting and supernetting is. Subnetting is just increasing the number of hosts, increasing the number of networks you have on your system by using some of your host bits. And supernetting is increasing the number of hosts you have by taking away some of your network bits. So now we get to the subnet mask. And so if you recall in this slide up here, 9, we have 4 bytes, right? And each byte is 8 bits. So this is 1 octet, 2 octet, 3 octet, 4 octet, or the first byte, the second byte, the third byte, the fourth byte, however you want to rationalize this. All in all, you have 32 bits in total. Okay, and recall that you are given a set number of network bits. This is your network ID, and then everything else is your host bits or your host IDs. So what the subnet mask is essentially a shorthand way of telling both the user and the computer what the network ID is. So what do we have here? We have FF00, right? Or in other words, the first 24 bits, if we are going from left to right, are all ones. And the last 8 bits are all zeros. Or not all zeros, are the hosts. So if we if we ORed this mask with the IP address, right, we would get a we would get a host. I'm sorry. If we ANDed it though, an IP address to a device. If we ANDed it though, we would get the network address. Because again, if we go up to here, when the host ID is all zeros, you were referring to the main network. This, you're referring to this network. And this is what is occurring here. If you get a subnet mask and then AND that mask to any particular address, you will get its network address. And so that's useful for routing, which is something that I will be going over in the next video because I think this is already long enough. Alright, and this is what CIDR is: classless interdomain routing. So instead of having class A, class B, class C, yada 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 yada, right, we allow users to buy a network that has a set amount of hosts and then just go off that, where we have A, B, C, D, which is each one of the octets, and then /x is the subnet mask. Alright, and obviously these are going to be, if you can do this, it's very straightforward. But if not, don't worry too much about it. This should be a homework problem, so if I have time, I will make a video going over exactly how to do this right there. Okay, next one, forwarding example. This is important to know, but it's also self-explanatory. If you get this IP address right here, right, 135.46.63.10, well, where does this one fall under? And then just check into here and then just send it to that interface. And that's basically how you do this. There's an example of this in a midterm, so I'll be going over this and that likely in another video. How does one get the network part of the IP address? Again, you just AND it. You have 20 right here, right? So if we go from left to right, we just go 1, 1, 1, 1, 1 all the way for the first 20, and then everything else is all 0. So then we AND it, and then we'll get the network. How does the ISP get block of addresses? ICANN, internet, yeah. This is basically the main organization that maintains IP addresses. Okay, at long last, we can hit the IP header. Now this thing is key. This is the most important part of this entire review. The IP header is going to be the IP is going to be a big chunk of your midterm too. And if you don't understand the IP header, it's very likely you're not going to understand IP at all. So first you have version, so IPv4, 5, or 6, but typically it's only going to be 4 and 6. 5 completely ignored. Everything before 4 so old and anarchic that it's not even used at all for actual any versions. Header length again is a maximum of 20 to a minimum of 20 to a maximum of 60. First service type unused. Total length of the IP packet. Identification is used for when the packet is segmented to identify which segment goes to what. Flags are shown in here. You either have the do not fragment flag set, the more flag set, or nothing is set. Fragment offset, as you can see, is only 13 bits, which has an effect later, and the flags take up 3 bits. Time to live, or TTL, this should be something very easy for you to understand because it's the same thing. Once TTL hits 0 and it's not at the place it needs to be, whoever has that packet drops it. Protocol is used to identify where the payload goes to, either to UDP or TCP or whatever else in the transport layer. Header checksum is again straightforward. You're gonna have 16-bit values or 2-byte values and add them all up, XORs, all that jazz to get to 0. Then you have the IP address, destination, source and destination IP address, and then the options. And here's some padding here. We're not going to go over the options at all. These are not going to be tested at all, at least in my exam. And so this is how reassembly and disassembly works in a nutshell. If the MTU is smaller than the packet you're trying to send, then you have to segment it. And so however you want to read it from, if it's coming from an upper layer protocol, then you get through the IP, it goes through the network layer into the IP, and then it processes it. If we need to route it, right, or fragment, not segment, I'm sorry, I've been saying segment this whole time, it's fragment. And if the MTU, it's too big, it's too small, then we have to fragment it, and then each fragment go their own way. Vice versa, if the fragment comes in through and it's to this particular node, then it gets to the reassembly module, and then they get linked to a table until all of the fragments are collected, and then it gets reassembled and sent up to the whatever transport layer protocol. Fragment and reassembly, MTU, yada yada, all that jazz. It's the same thing. It's pretty self-explanatory. Okay, so IP fragmentation. So this is very easy to understand once you get it down. So here you see the flag set for more fragments. So this is saying there is no more fragments for this particular packet, right? And this packet right here has a payload of 4,000 bytes. Data of 4,000 bytes. Payload or data, whatever you want to say. So the total length, we assume it to be a header of 20. So the total length is 4,000 plus 20, so 4,020. Right? And this is the identification number for this particular packet. And then it hits an MTU where it has to split up. So in this case, the MTU is a maximum of 1,420. The reason we can tell that is because the packet size, the packet length here is 1,420. Now, if the MTU was 4,000, then that means that the payload, instead of being 1,400, must be 1,380 or 1,380, because the header is included in the MTU calculation. Okay? What it's not included in is when you separate the payload. So as you can see here, the payload is 1,400. So if you do 1,400 divided by 8, you get 175. So that's what you get here then is 3. You only get 13 bits to represent 16 bits, right? So how do we do that? Well, we work with shifting, right? Because if you shift to the left, you're dividing by 2, if I recall correctly, but if you shift to the right, you're being multiplied. And so we use shifting mechanics to basically ensure we get the correct number. In this case, we want to multiply by 3, divide by 3, and multiply by 3 to get the values back and forth. So 1,400 divided by 3 gives us 175. So this is saying we start from 000 and we go up to 174. So the next fragment must start at 175 and end at 349. And the last the last fragment must start at 350, and then that's it. Now, as you notice here, all the identification numbers are the same, and that's because it comes from the same packet. This is so that when you go back into the reassembly module and the reassembly table, you know which fragment goes to where. And then here you see the the more flag set is set to 1 for each one except the last one. Okay? And this is the case. If you are fragmenting a fragment that already has the flag set, then it inherits the do not frag. The flag set for more fragments. But if the very last fragment is being fragmented, right? The way that it works is really it's more of a service, a netcode thing, but I would assume that the way it works is it fragments it sequentially, because it does, and the very last fragment that gets the rest of the payload gets assigned the no more fragments are coming, or in other words, this M is set to 0. The more fragments flag is set to 0. If you understand what I'm saying there. Basically, you fragment sequentially, and the very last fragment gets the 0 in the more flag. This is very straightforward. If you can follow this image right here, then any example I give at you will be very easy to do. And I'm also going to cover exactly how to do it in a math related one in another video. So ICMP, here ICMP, the main thing that you have to look through is recall, echo, fragment, echo request, and TTL. And if you just go over the stuff highlighted in red, that's basically all you need to know for ICMP. ICMP format. ICMP is basically a protocol encapsulated in an IP packet. So most of the stuff is the same, but I would say look over it. There may be a question on it, but it's more going to be related to this stuff here rather than the formatting of it. DHCP. DHCP, the only real things that I would focus on is the discovery, offer, request, and ACK here. Also know that DHCP is a application layer protocol. The reason why we cover it in the network layer is because, well, you need an IP address, and it's better to talk about it in here when we're talking about IP addresses. Do note that when you are doing a DHCP offer and discovery, it's always broadcast, whereas in request and acknowledgement, technically you can do a unicast here, but typically you just want to and nowadays typically it is a unicast, and the way that works is through MAC addresses, but we haven't covered that yet, so just know that everything is a broadcast for right now. And this is fairly straightforward. It's like three-way handshaking in TCP. If there's a question on it, it's probably going to be on DHCP. It's probably going to be related mainly on this stuff right here, and understanding that these dynamically assigned IP addresses are leased. They are not owned by the device that's being assigned it. And this is just another technique to handle the consequences of classical addressing. Okay, so this image here, we have a new client that joined and needs an IP address, so it does a broadcast to the DHCP server. and then the router gets that request and go, hey, this is a broadcast, so I'm going to forward it to the DHCP server. DHCP server is going to broadcast back, and that's going to get transmitted back to here, and it's just going to be this entire sequence like that. I was going to say natural network address translation. So this one is even more simple to understand, in my opinion. It's fairly straightforward. You have the local network and then the rest of the internet. And again, as I explained before, when you are talking to people over, or when you're sending things over the internet, you're sending it to the assigned IP address that you paid for or you were given by your ISP or whatever. But the moment that packet hits your private network, then you can assign any IP address to any of your devices. And that's what NAT is doing. Your router or whatever is connecting you to other networks is assigning a specific port number from their device, plus the public IP address, and mapping that to a particular device on the private IP address. And in my opinion, that's as straightforward as I can get there, and all of it's going to be conceptual if there are questions on that. We aren't going to talk about implementing it. There may be issues that that you may want to read up here. That may be part of the questions, but understanding how the table works and how the translation works is the more important stuff, and the issues. Alright, I'm not going to ARP. I'm not going to go for the quizzes. So that's it there. That's going to be it for this video. Routing will be its own video. Because it's, yeah. Routing will be its own video. And likely, actually, I might not make a video at all, depending on... Yeah, but yeah, that's it for this video. Hope you guys got a nice review out of it. But the next videos will be on routing and the previous midterms.